At this limit, I realize that when x approaches infinity, so first of all, I have to see what this limit is all about. When x approaches infinity, which of these three terms is the most powerful? We are talking about infinity.
The numerator.
Say it again.
The one on the top.
Which of these three terms is the most powerful when x approaches infinity?
4x squared.
Of course, that's the most powerful. Where is 4x squared going when x approaches infinity?
Positive infinity.
Very good. So all this goes to infinity. Which of these two is the most powerful when x approaches infinity?
X squared.
Good. Where is this going then?
Also positive infinity.
Very good. Okay, so when in the situation of infinity, we know that this is an indeterminate case. We cannot write anything. But what we can do, write limit as x approaches infinity. And as we did before, what is the degree of the numerator? What is the degree?
Second degree.
Good. So we factor out the degree. So I have three terms. I have to come up with three terms here. X squared times what is 4x squared?
4.
Very good. Plus x squared times what is 2x
2.
over x. X squared times 2 over x, you simplify an x and you get 2x. Is that okay?
Yes, it is.
Good. Minus x squared times what is negative 9, or 9 in this case because I already put the minus.
Nine over x squared.
Very good. Awesome. If you have any doubts, x squared with x squared will go away and you get negative 9 back. Awesome. Thank you. Same thing in the denominator now. What is the degree of the denominator?
Second degree.
Good. So I have to factor that. So see, I'm working on those independently. X squared times what is x squared? I know you're going to say 1 plus x squared times what is 16?
16 over x squared.
Good. Of course, this was the whole purpose. And now let's identify where these are going. Where is this going when x approaches infinity? Where is this going when x approaches infinity? Where is this going when x approaches infinity?
I see both sides are going to 0.
Excellent. So then the limit is
0. 4.
very good. There is only 4 left at the top. There is only 1 left in the denominator. 4 over 1 will be 4, which means y equals 4 is the horizontal asymptote. Every time we investigate infinities and we get a number, if the limit is from a function as x approaches infinity or negative infinity, and the answer is a number, then this is a horizontal asymptote. Good. So now let's go back to 23. Okay, well, I have to plug in. Well, 25 plus 25, this is 50. But 5 minus 5 is 0. What do we know about a number over 0? What are the options for a number over 0?
DNA.
No. There are 3 possibilities. One of them is indeed DNE.
A vertical asymptote?
Infinity, negative infinity, or DNE. Yes, in this case, it will happen to be a vertical asymptote. So please remember, a number over 0 can be infinity, negative infinity, or DNE. Because the limit is not from left or right, I must investigate left and right. I cannot make a decision here yet. I don't know what to write because the limit is not from one or the other. It's from one or the other. So I have to find limit as x approaches 5 from the left. I have to find limit as x approaches 5 from the right. If they are both infinity, then I write infinity. If they're both negative infinity, I write negative infinity. If one is infinity and the other one is negative infinity, then I write DNE. So x squared plus 25 over x minus 5, x squared plus 25 over x minus 5. So 5 from the left means 4.9. 4.9 minus 5, this is always a positive number. 4.9 minus 5, this will give us a negative infinity. 5.1 minus 5, this will give us a positive infinity. And now I can conclude that this is DNE. If I were given from the beginning either plus or minus, then I don't need all this analysis. I'm only asked one or the other. In this case, positive, then I'm asked this one. But I wasn't. I was asked to make a decision from either side. Well, I have to find this one, I have to find this one, and if they're not the same, then I write DNE. I know they will be infinity. But I have to check if they're both infinity, then I write positive infinity. They are both negative infinity, then I write negative infinity. But they're opposites. They're not the same. So then I have to write DNE. I cannot write DNE before I investigate these two because the limit is from either side. And this is identical. I would like now to change this into negative. So this is the same thing. But this one is just, it does not require investigation on both sides because it's only from the left. It's still a number over 0. But from the left with 2.9, this will be simply negative infinity, and it's done. But if I change that problem, let's say, just to look at a different situation, as x approaches 5 from x squared minus 25 over x minus 5, then this has 0 over 0, and there is hope. I don't know for sure, but there is hope. 0 over 0 has hope. Even infinity over infinity has hope, and it did, 4. So I realize that I have to factor the top into x plus 5, x minus 5. And I'm so happy because the whole thing, the problem goes away. This is the problem. When I move 5 to the other side, I know x minus 5 is the problem because x minus 5 approaches 0. That's where 0 over 0 is coming from. So then 5 plus 5 is 10. This is not a horizontal asymptote because this is not infinity. This is just a number. Good. The topic of limits was good. Thank you for picking that for discussion as a topic. Anything else from here? Or we look at test 2. Anything else? We know how to graph a piecewise defined function. We know how to find domain. We already know this. We had it again on test 3. Difference quotient, right? And the definition of the derivative as the limit of the difference quotient. The definition, f prime. The limit as h approaches 0 from the difference quotient, f of x plus h minus f of x over h. Differentiation rules, acceleration, velocity, average revenue, cost, and profit. Do we want to look at anything else here? Okay, so let's look at test 2 then. If you decide to take that bonus on Sunday, let me know so I know who to send the link to. I already have 1, 2, 3, 4 people. Okay.
You just want us to email you
Yes.
and say that we will do
Yes.
it?
Yes.
Okay.
If you want to. If you don't need to, you don't have to. This is not. It's only for those who want to raise their test 2 grade. Okay. Let's look at.
Professor,
Yes.
did you send the email about the bonus?
You just have to tell me that you want to participate, and I will send you the link on Sunday between 6 and 7. We have 1 hour for 25 points.
Okay, thank you.
You're
And
welcome.
Professor, in your email, you said the bonus points was for test 3.
No, it is only on test 2.
Okay.
Is that what I said?
When I read it, yes. I may have read it wrong.
I think I was talking about test 3, but the bonus is on test 2. But I will send out an email again just to make sure.
Yeah, it was test 3 bonus is what you named it.
Okay. I'm so sorry. My
No worries.
apologies. I will make the correction. Okay, so test 3. I did not have a list on test 3. Maybe I had it on the previous class. Oh, test 2. What did I do here? I always like to present a list. Well, maybe it was on the previous. Test 2 review. Huh. Also look at, if you'd like, look at the study groups. There are a lot of problems solved there. Okay, let me see. Let me see here. Test 3, test 2, I'm looking for. Okay, I just want to see here if I made a list. If not, we can make a list right now. I'm just looking at the lecture notes. Implicit differentiation, graphing. Okay, so I did not make a list, but it's exponentials and logs, and chapter 3 except 3.7. Implicit differentiation, related rates. Okay. What would you like to look at? Graphing. So this was all implicit differentiation basically, or differentiating an equation, keeping in mind that all these, that's why I put a dot underneath them, all these are functions, and they're all functions of time. This was a volume situation with a sphere, I think, then with a cube. Okay, so let me know, chapter 2, chapter 3. What would you like to work on?
Can we go over a graphing question?
Yes, yes, very good. So this is chapter 3. I'm going to choose, unless you have a function for me.
No, you can choose.
Okay, I will choose. Okay, I can make one up, but I like to choose. Yeah, a simple one, like negative 8x, number 19. I picked 19 on page 376. And this is f of x equals negative 8x over x squared plus 1. And let me let you choose because I don't remember if we did this problem. If you think we did, then we can look at another one, something like f of x equals x e to negative 6x, and this is number 20 on the same page. So you choose whichever you want.
Can we do the number 19?
Number 19. Very good. So for number 19, I will look at it as if it looks like this, or it's presented like this. It's the same thing. It's easier for differentiating, it's easier for finding x-intercepts, and much better. If I have here plus 3, I can't do that. But it's a factor in the numerator, and the factor in the numerator is the same with the factor outside, multiplying the whole thing. It's the same thing. Okay, so I will start my table with f prime, f of x, and the second derivative. I realize that this is never 0. So this function will not have vertical asymptotes defined everywhere. 0 has to be in the table. So 0 at the top and 1 in the denominator makes the function 0. There are no other x-intercepts. I need to determine the limits. And then I'm done with the function, and I will move on to the first derivative and then second derivative. So I have to find the limits, and I have to write them. Limit as x approaches infinity from, I can put negative 8 outside, so it doesn't bother me in there. It doesn't matter, you can put it inside too. So the numerator goes to infinity, the denominator goes to infinity. But I know one thing here, that this is much smaller than this. At any point in time, approaching infinity, this will be much smaller than this. So then what is the limit?
Zero.
Very good. The limit is indeed 0. So y equals 0 is a horizontal asymptote. I don't have to write the next one because it's the same thing. So 0 here, 0 here. I make myself a note. Y equals 0, horizontal asymptote. Perfect. Now I move on to the first derivative. So f prime equals negative 8. Now, it's a ratio, it's a quotient, so I have to use the quotient rule. The top prime is 1 times the denominator minus the top times the denominator prime over the denominator squared. So remember, 1 over 2 prime equals 1 prime times 2 minus 1 times 2 prime over 2 squared. So then I continue. Every time I find out something else, I come back to the table. So this is negative 8. Negative 2x squared plus x squared is negative x squared and plus 1 over x squared plus 1 squared. I hope you are allergic like I am to negative leading coefficients. Pull it out. 8 x squared minus 1 over x squared plus 1 squared. Yes, I will factor out the numerator right away. And when I set this equal to 0, I know that a fraction is 0 only when the top is 0. So I get two options, and they are 1 and negative 1. Negative 1, 1. At this point, I have to find these values. So negative 1 is positive 8 over 2. 1. Negative 8 over 2. I need to study the sign of the derivative. I will plug in 0 in the derivative, and I get negative 8 over positive. I don't even need to plug in anything here. This is always positive. When I plug in 0, I get negative When I plug in negative 10, I get positive. When I plug in 10, I still get positive. At this point, I need to make sure that this row and this row are in sync. If they're not, I'll say, oops, I have an error somewhere. So from 0 to 4, the function is increasing. Yes, it is. From 4 to 0, the function is decreasing. Yes, it is. From 0 to negative 4, yes, it is. From negative 4 to 0 is increasing. Yes, it is. I already know that this is a relative max. I already know that this is a relative min. Why? Because of the sign change of the derivative. Why? Because of the sign change of the derivative. So then if this is a relative min, I expect that the second derivative to be positive here, and I expect the second derivative to be negative here. We'll see. Okay, now the second derivative. I will differentiate this function, not this. It's more difficult to differentiate. So I'll differentiate, keep 8 outside. Okay, the top function prime is 2x times the denominator, squared plus 1 squared, minus the top times the denominator prime, 2x squared plus 1 times 2x, the inner function prime. You should always say times the inner function prime, over x squared plus 1 to the 4th power. Again, I always say this in my classes. If you're tempted to simplify these two, the whole thing will collapse. And from this point on, everything will make no sense. So we have to factor as much as possible in order to simplify. Factor out. What am I factoring out? 2x. And I'm factoring out x squared plus 1. 8 stays outside, waiting patiently. 2x is out, x squared plus 1 is out, and let's see what else is left. 2x is out, one of these two are out, one is left. Minus. This is out, this is out. 2 times x squared with minus in front. 2 times negative 1 with minus in front. Let's stop for a moment and see if you have any questions here. Any questions so far? Now, only now I can simplify because I'm simplifying factors. 8 times 2 is 16. So x negative x squared plus 3 over x squared plus 1 to the 3rd. Negative outside. X squared minus 3. When I set the second derivative equal to 0, I will get x equals 0. But also from here, I will get two solutions, plus or minus the square root of 3. So now I study the sign of this, but definitely not the denominator because it's always positive. Okay, so when I plug in negative 10, and of course not this one, I don't care for it. So this is negative with negative in front is positive, and also positive, 10 squared minus 3. So positive, positive, everything positive on this side. Okay, on this side, because it's a maximum, I'm expecting the function to be negative. So I'm plugging in negative 1. So this is positive, but this is negative, because this is negative 3, and this is positive. Then I plug in 1. Negative here and negative here, so positive. And then I plug in 10, negative, positive. So it does not hold water as expected. It does as expected. It's a minimum. And it does not. Okay, I'm ready to graph. I don't care about anything else but my table. Nothing else makes any change. I don't care for anything else. Okay, so here's my graph. Okay, -1, 4. I plug in the points first. -2, so this is here. -1.7. Oh, I didn't determine this value, and I didn't determine this value. Okay, so with -3, I need to plug it in. So I'm going to share my screen because I need an approximation. I would not know where to plot that. So I will put my function in here in -8x and divided by parentheses x squared plus 1. And the function is odd, so they have to be the same number but opposites. Okay, so negative the square root of 3 and positive the square root of 3. As expected, so 3.5 and -3.5. So 3.5, -3.5. I put them in my table. So here so positive 3.5, 3.5 here, and this is 0, 0, 0, 0, 1, -4, and the square root of 3, -3.5. So the function approaches the horizontal asymptote, opening up and increasing to 3.5. So this is an inflection point. Changes concavity, increasing to the relative max. Decreasing, opening down to 0, 0. Inflection point, changing concavity at 0, 0, opening up, reaching the minimum. Continue to increase to the inflection point, opening up. Changes concavity, and then it approaches opening downward, approaching the horizontal asymptote. So this is f of x, 8x with minus over x squared plus 1. Again, if you want to see this table over and over on many, many examples, let me share my screen. You will find it not just in these lecture notes, but in previous semesters. I'll show you where they are. And the graph is section, it's over several sections to be honest, but it's in chapter 3, right after discussion of the first and second derivatives tests. So 3, 3, 3, 4, yeah, yes, 3, 3, 2, 3, 3. So if you want to go to the previous lectures, just to work on some other problems, they may be in chapter 2 just because the book changed the order of some sections. So since this is the old book, it may be here. in chapter 2. Yeah, these are the closed interval or just relative max, relative min. These are the beginnings of that. And the second, and yeah. And I explain here, and this is the table again, on which function, on this function, with all the steps and what they mean. Oh, look at that. Gee. But I think I just didn't get the chance to finish this one. So I'm pretty sure it continues in the next section. Let's take a look.